All right, welcome. Let's go ahead and take a look at an example from crystallography. It'll require us to look at some matrix math, so we'll kind of review that real quick, and we will then create a function to perform a unit cell volume calculation, and then we'll look at how to sort of package that function if you want in its own cell with its own import commands that we can copy into a text file that we can then later import into any notebook that we have and have those functions available to us, just like we import any other package. So we're going to create our own functions for import at a future time. All right, so with matrices, the main thing we're going to be looking at and using is the NumPy Lineage module. Okay. And so I've got a link here for you, and I'll post this file that you can take a look at some of the matrix math that goes on. If we don't do it here, like well, actually we're going to take a look at the dot product and we'll look at the determinant. But you can take a look at that. All right, let's go ahead first, and we're going to import NumPy. That's all we need for today's lesson. So we're going to go ahead and import NumPy. And then, as usual, in sort of a convention now, we're going to go ahead and import it as NP. So all this does is rename NumPy to NP, so I don't have to type out the full NumPy every time. I can just type NP. So that's all that that's doing, but the import command is bringing in that NumPy package. All right, so let's go ahead and we will define a matrix in NumPy. And so we're going to do that by simply using a NumPy array. So a matrix is just NumPy array. Array is a function, and so we're going to use the parentheses here. And then to define the array, we're going to simply make a list of lists. These are really arrays since we're in NumPy, but they look like lists. And so this is our first row, our second row, our third row, etc. And then this is the bracket that contains all of our rows. Okay. And again, these are just the parentheses that belong to the function. They're not actually part of our matrix that we're creating here. So let's go ahead and just put some numbers in. I'm going to put in 1, 2, 3, 4, 5, 6, and 7, 8, 9. Not very original. And if I go ahead and run that, again, Shift Enter, you can see the output. It just tells us that we've created an array. And here's the first, second, and third rows. Okay, so that's our NumPy array. All right, so let's go ahead and call this something. I'm going to call it just matrix A. And we're going to go ahead and also make a matrix B. I'm going to save myself a little writing by just copying this. All right, maybe we can come in here and I'm just going to add 1 to all the numbers just so it's different. And I run that again. And then notice that there's no output. Right. When I do this assignment, by default, there's no output from that cell. And so the way I can get an output, for example, would be to just say B, run B. There's B. Okay. If I try to run B, which is fine, and A, what you'll find is I only see the last output. Okay. All of our cells here in Python by default only have one output, and it's the last output. So if I want to get more than one output, then what I want to do is just say print B. Okay, so that'll now show up, and then A will still be the output for the cell, so I don't have to put a print around that. But you can see the difference. A here is showing you the variable, which is an array, and then the print command is just giving you the output view. So, all right, so let's keep going. So if we're going to multiply matrices using the Lineage module within NumPy, and what we're going to use here is the dot product. So it's a dot product of the matrices. I'm going to go ahead and create another cell. And now I can simply say numpy.lineage dot, and then dot simply just takes the two matrices and I'll put them in the order that I want them to be multiplied. A dot B. All right, then I get this error. Lineage has no attribute dot. Okay, so let's see. What did I do wrong? I don't see anything obvious first. So actually, this brings up a good time to go ahead and use help. So I'm going to do is just do a simple Google search on dot product in NumPy. So here it is, NumPy dot. Okay, so what this actually is showing me, I can scroll through and take a look at an example. Here's a dot product with just scalars. Here's one that's using matrices, right? But you can see that it's just NumPy dot AB. So my mistake here is that actually multiplying matrices, the dot product command is actually just a part of NumPy, not the separate Lineage. I was getting confused there because the Lineage module is actually where we're going to find the determinant, which we're going to do in a minute. Okay, so this is a markdown cell, by the way. When I click in it, I can use this markdown language, right? Notice it's a markdown. So this is cells that won't be run, and these allow me to define headers. So this would be a big header, a little bit smaller, a little bit smaller, a little bit smaller. And I run the markdown cell by doing the shift enter just like I do the others, and so there we go. All right, so let me go ahead and get rid of the Lineage piece, and then all should be good. There we go. All right, so that's how to multiply them. So let's go ahead now and look at a specific example. So we're going to take a look at the G matrix used in crystallography. So for a general unit cell for crystal structure, we would have a triclinic unit cell. Hopefully you remember some of this from 2044. And that cell would have a lattice parameter A, B, and C, and angles between these three different directions of alpha, beta, and gamma. Okay. Notice alpha is the angle between B and C. Right. Beta here is the angle between C and A, and gamma is the angle between the axis B and A. All right. So this is the G matrix, and this is the way it's defined. So you can see here A squared, B squared, C squared along the axes, A times B, this is times the cosine of that angle there between them. A times C, cosine beta, which is the angle between them. Okay, so that's my G matrix. So let's go ahead and develop the G matrix and look at the specific case now of white tin, which is tetragonal. And white tin has lattice parameters of 0.583. Okay, that's for the A and B axes, so they're equal, so a square base. And then it's stretched in the C axis. Okay, but the angles are all 90 degrees. So basically we're taking a cubic structure and we're just stretching it now in the C direction. And that's our white tin. Okay, so let's go ahead and create this G matrix. So this is going to be, let's say G is equal to NumPy array, right? Just like we did before. And then our array is going to, whoops. So now we're going to have our array defined as an array of 3 arrays. So see, count on my brackets. Yeah, it looks good. So I just got the format set up, and then I'm going to go ahead and put in the values. So I have a squared, so that is going to be 0.583 squared. If you're new to Python, or you don't remember this from last time, the power is a double star. And so there is no caret for power in Python. It's the double star, so that means power. All right, and now the angles are all 90 degrees, alpha, beta, and gamma. So the cosine of 90 is 0. So that means all of my off-diagonal terms are all going to be zeros. So I'm going to have 0. And now this is b, which is the same 0.583 squared, 0. And now the bottom is 0, 0. And then c squared, which is 0.318 squared. Okay, so let's go ahead and run that, and I want to see an output. Okay, good. So there's my a squared, b squared, c squared for my G matrix. All right, so let's go ahead now and find the volume of the unit cell for tin. Okay, so now the volume for the unit cell for tin is straightforward because all the angles are 90 degrees. So I know that the volume of this unit cell should just be the volume of this box. So A times B times C. So that's 0.583 times 0.583 times 0.318, okay, all nanometers. Okay, so there's the volume of the unit cell, but we want to use the G matrix method so that we can make our function, and we can do this for any unit cell for any crystal structure. Okay, but I just want to do that. This is a good test, so now we know what the answer should be. Okay, so let's go ahead and find the square root of the determinant. Okay, so that's the definition for the volume of a unit cell is the square root of the determinant of the G matrix. All right, so square root is numpy dot square root. Okay, and hopefully you're getting used to this dots notation. Right, this tells you what package you're calling. This is numpy, and then dot then tells you what function or module you're calling within the package. So I'm going to call the square root function, which exists in numpy. All right, so that's my square root, and then I want to do the determinant of G. So within now my square root brackets, I'm going to go ahead and do the determinant. This is the one that's in the Lineage package, so I should be okay now this time. So I've got within numpy, there's a separate module called Lineage, and then within that Lineage, there's a function called determinant. So I'm going to go ahead and do that for G, and let's run that, and I get the same answer back. So great. So that worked. All right, so that's how you find the volume of the unit cell. That's how you use the determinant function and the square root function. All right, I'm going to actually pause here because I don't want this video to get too long, and I'm going to come back after a short break, and then we will tackle our problem essentially that's close for homework, which is writing a function to now perform this calculation, accepting any lattice parameters that are given to it, and then what we're going to do is take that function and eventually put it into a text file that we can then just call. Okay, so I'm going to go ahead and take a break here, and I'll see you in a few minutes.